We've already seen that we can build approximations to a function by using a locally linear approximation or a local linear approximation. And the two forms that we've seen are the function itself is approximately the value at a nearby point plus some changes due to a little move in x and a little move in y. And we could also represent that by bringing this term here, f of ab, over to the other side, so we get f of xy minus f of ab. And so that's a difference in function values, and we can write that as a result of, or a function of, a small change in x and a small change in y away from the starting point that we selected. Sometimes people use a different notation for this. They talk about the delta x and delta y getting smaller and smaller, and what that does, of course, is turn the approximation into an equal sign, and typically we turn the deltas into d's and you call them differentials. Now, nothing's actually happening here except we're replacing deltas with d's, and the equals, or the approximation, becomes an equal sign. In practice, we still use finite values for dx and dy for most cases, and this becomes back an approximation, but we just wanted to introduce this notation because it is commonly seen in applications later on in life. Most people in practice think of this as a change in f, so delta f, for very small changes in x and y. What this leaves us with is, for three functions of three variables, there we go, the formulas that we have are linear approximation, so the value plus the x slope, y slope, z slope times x, y, z differences, or written explicitly as differences, gives us the change in f, and again that change or alternative where we replace the delta with a d and the approximately equal sign with an equal sign. This is most often used in theory. These two formulas here are much more frequently used in practice. We'll see later on in this unit how we might actually apply this to specific examples. In fact, we're going to look at error bounds as the next part of the course.